Hi you guys, so today we're taking a look at the reaction profile diagram, and if you guys look in your notes, it's section 5.6. It's right after steady state approximation. So I'm going to go ahead and go take a look at some of these graphs with you guys. Reaction profile, basically it's a way to take a look at the energy that is, the potential energy that your reactants and your products have during a chemical reaction as time passes by. So you could see our x-axis is looking at the reaction progress, which is what's happening from left, the reactant side, over to the right side, to the product side. We have a few parts of this graph that you guys want to take special note of here. The reactants are labeled on the left side. The products are over on the right side, and you could see there's this little hump that has to be overcome for the reactants to turn into products. And we call this little part right over here our transition state. All right, so if you're looking at this reaction here of A plus BC, and then on the product side, it looks like AB are forming a bond and then C is left by itself. Those are the products. The transition state is what occurs when a collision happens between the molecules of A and BC. And it's this part where they're all kind of together, usually in some sort of orientation where the bonds are going to break and the new bonds are going to form. And we know for that this transition state, it's a state where it's very, very unstable. The graph looks like it's in this transition state for a really long period of time, but it's a little short time period where everything is together and they're either like twisting or they're bent, or it's this unstable configuration of the reactants that we have over here. This difference between the reactant energy and the transition state, we call this here our activation energy, which you guys have seen before. And we call this just the energy of activation. So E sub A is what you guys are seeing over here. And this is the energy that the reactants need to overcome in order for it to make it over to the product side. Okay, so this slide over here is defining actually the activation energy that we said, but the amount of activation energy that a reaction needs in order to proceed is pretty much just the difference between the reactant energy and then this transition state that we talked about over here. And when you're in the transition state, the reactant molecules, the A, B, and C, it's called the activated complex over here. So this is when the molecules in play are actually like together before they break off and turn into the product side. We also talked about before that not all collisions actually lead to product formation, right? So the collisions themselves, they have to have enough energy for the reactants to actually break up the bonds and then to form the new bonds for the product side over here. So this collision having enough energy is really important. And you could imagine if this hump were a lot lower, right? Maybe the activation energy is a lot less. So we reduce it from here to here now, right? Then a lot more of these collisions are going to be able to make it over the hump and go over to the product side. So what it essentially does is you speed up the rate of the chemical reaction because more of those collisions that you're starting off with end up making it over to the product side because the energy needed to make it over the hump is so much less than what it was before. We also have talked about catalysts in our unit, and on Monday we'll be doing a lot more work with catalysts, but this is basically what catalysts do. They take that activation energy state and they lower the requirement for the energy state of the collision so that a lot more reactants are essentially turning over into products here. We could calculate this activation energy pretty easily. You just take the energy state of that transition state right here, right? So that's the energy of the TS, and you subtract it from the energy of the reactants, right? So it's like this difference right here that is your activation energy. And if you wanted to see what it looks like for the reverse reaction to happen, so like the products turning over to reactants, right? So we're going from the other end. You're still starting off with the transition state, right? But now you have to subtract the energy of the product state. So this is for the reverse reaction. And you could see that for this particular reaction, it's a lot harder for the reverse reaction to happen. The activation energy for the reverse is a lot greater than the activation energy for the forward one that you looked at with me right here. We also looked at these graphs last year. I don't know if you guys remember it, but we talked about exothermic and endothermic reactions in terms of these energy profile diagrams that you see here. And by definition, you guys remember that an exothermic reaction is one in which energy is released or given off from a chemical reaction, and an endothermic reaction is where energy goes in, or the reaction absorbs energy to actually occur and make it over to the product side. And that delta H value, you guys remember back from our equilibrium unit when we're talking about positive and negative values of delta H. You could calculate this by using this reaction profile, and it's always just products minus reactants, which makes sense, right? Because it's the change in enthalpy. So you look at the energy of the products minus the energy of the reactants. You could see when you do that for this graph that you guys see down here, right? So the product energy is a lot lower than the reactant energy. And when you do that, you end up with a delta H that is negative over here. Or this graph here is really describing for us what an exothermic reaction looks like. Whereas on this end, I think my face is covering off some of the graph here, but you have reactants at a lower state of energy than the product energy that you see over here. So if you were to do the delta H calculation, you would go product energy minus reactant energy, and we could see here that our enthalpy would be a positive value, and this is depicting what an endothermic reaction profile would look like. And you could see here between the two reactions that we have, right? So this is what our activation energy looks like for an exothermic reaction. And this is what our activation energy looks like for an endothermic reaction, right? That huge increase in activation energy can be explained by the fact that we actually have to put heat in for this chemical reaction to occur and turn over to products. We have also learned this idea of there being many steps inside of an actual chemical reaction, and those are called our elementary steps. And we said that if we know what the steps are, we would call that the mechanism of the actual reaction itself. These reaction profiles are also really useful for us because you could actually look at the profile and have an idea for what the reaction mechanism looks like as well. So one of the key ideas here is that the slowest rate determining step that you have in your mechanism is slow because there is a really, really high activation energy associated with that step. Right? So if you look at this little diagram that you see over to the right, and I think we have this one, yeah, you guys have this right in your notes over here. We don't just have one hump here, but we have two activation energies inside of our reaction profile. And we could see that there is a reactant, there's an activation energy here occurring for reactants and products, and then you reach this product stage. And then from here to here, there's another activation energy right there. So we have EA1 and we have a EA2, right? And what this profile is showing us is this is a two-step mechanism that we have, meaning two steps, right? And then for our very, very first step, there is a really high activation energy. And for the second step, we have a small activation energy. So we could tell that this guy right here is going to be the slow step. It means that the collisions that have to occur for step one have a lot more energy requirement, right? So the collisions, they need enough energy to overcome this activation energy, and it's a lot higher than it is for EA2. So we could see just based on the graph and the activation energies that are provided that the step one is going to be our slow step. So how does temperature play into all of this here? So if you guys are looking at temperature, right, what that essentially does, right, is temperature is going to provide more energy to your reactants or your particles that are going around and colliding with each other, right? Or another way that we could state this is that your temperature change, right, is going to be proportional to your kinetic energy that you have of the molecules themselves, right? And you might remember back from our equilibrium unit, this is also true, but remember how temperature is really the only way that you could actually get a change in your K constant, right? Well, the rationale for that is that your equilibrium expression comes from rate loss. It comes from products over reactants here, and we have these little K's like built in to our equilibrium constant. And what really occurs is as you increase your temperature, right, that K value is going to change as well, right? And remember this, the lowercase k, it's kind of giving you guys an indication for speed. The larger the value of your K constant, it's telling you that your reaction's faster. And then the smaller your K constant is, it's telling you that your reaction is a slower one. So if you have a way of directly impacting that constant by changing or playing around the temperature, it's going to do something in terms of what is happening chemically or what is happening kinetics-wise to the reaction over here. So one thing to note, this is a key idea as well, is that your temperature change, it's not actually changing the mechanism. So it's not that it's going from like 3 steps to 2 steps or 3 steps to 1 step, right? So the energy of the transition state itself, right? That hump, the activation energy that you need for the reaction to proceed, that doesn't change at all. So this graph that you guys see over here, it's called the Maxwell-Boltzmann graph. Boltzmann graph here, and it's showing you a relationship between collisions and then also the energy that you have inside the chemical reaction. And collisions just mean like the number of collisions that occur, right? So I want you to look at with me 3 different temperature states that we have. So let's say this is like happening at room temp. We're looking at like 23 or 25 degrees Celsius. This one we move over to like 50 degrees Celsius, and maybe for temperature 3 we go to like 75. So we're going in even increments of 25 over here, right? So for our temperature 1, we're at 25 degrees. You could see that this is describing the kinetic energy of our molecules that we have here, right? The number of molecules under the curve for temperature 1, temperature 2, temperature 3, that's not changing, right? The number of molecules will stay consistent, but it's the fact that the curves themselves are flattening out. So this one over here, let's look at T3, is a graph where you could see the curve actually flattening out, right? And the number of molecules again is the same, but what you could see is that you end up with more molecules that are passing that activation energy line that you guys see over here, right? So when you are dealing with a hotter temperature, the collisions have more energy, and more of those molecules make it past the hump of overcoming activation energy to go ahead and turn over into products, okay? Catalysts, again, we'll be looking at in more detail on Monday, but one of the things that catalysts can do is they could change the pathway by just lowering the activation energy requirement needed for the reactants to turn into products over here. So you have an example here of a reactant turning, products are way over on the other side, just like where my eyes are right here. So reactants are turning over into products over on the other side. If you don't have a catalyst for this chemical reaction, you could see it's this purple hump that is your activation energy that needs to be overcome for the reactants to turn into products. So you could see like this is a pretty big activation energy, so not all the collisions are going to be able to make it past that and turn into products. So a lot of them might collide, but still like nothing occurs, right? But in the presence of a catalyst, what might happen is you guys might now change the mechanism. So you now go from a 1-step reaction pathway over to here, we're seeing like a 3-step reaction pathway, right? And the activation energy for each of these steps are so much less than that large activation energy that you saw for the uncatalyzed reaction here, right? So we do have multiple steps, yes, but the steps themselves are going to go so much faster because the activation energy requirement is so much less than what we had for the catalyst. And on Monday, we'll look at, well, like, how does this actually work, right? How do catalysts really lower that activation energy? And that's what we'll be looking at together on Monday in class. And then that all will lead us to the end of our little short kinetics unit. All right, thank you guys. Bye. For homework tonight, it's not too much. You guys have 5.5 and 5.6 you-do problems to do where you guys are going to be drawing some of these different graphs out given different energies, and I have a feeling you guys are going to do okay with it. All right, I'm done.